Well, here we go. This is going to be a pretty quick crash course in the introduction to waves. These are our colors that we're going to use today. And a lot of this you probably, hopefully, have already seen in, for example, physical science. And so I want to start just with the idea that if we draw a wave here, this is going to be the origin, which is a less common term for waves, but that's where the wave's going to start. So we assume that there's a spring or a rope, for example, some kind of medium. And we'll talk about what a medium is and what a wave is actually also. So the idea is that we have some medium that can carry the wave. And if I draw this here as consistent as possible, that's your experience with waves, that there's peaks and troughs, and so we should probably indicate that. So this would be a trough, the low point, and then this is a peak, but it's also known as a crest. And so this is the displacement from here. We could refer to this as the amplitude, right? And that's the height of the wave, kind of. Actually, the wave height is from top to bottom, but usually we only need to know the displacement from the origin. So you could imagine that you put a letter A there for the amplitude. Now, in and of itself, this is not complex for you guys, but we need to have some basic understandings of this, because when we get into sound waves and light waves, a lot of these references are going to be used. I want to go back to, we'll come back to amplitude in a minute here. The general idea of a wave is that from one position to the next identical position is called the wavelength. And that's the Greek letter lambda. And the reason we use that is because if you use the Greek letter lambda, it's because the letter L has been used, the English letter L is used for length with sound. So lambda is generally used for, it could be sound or light. Okay, but generally here when we have L should be for, it can be the length of a sound column, but it's also used for the concept of linear expansion and so on. So we just have to be careful, because you could use the letter L or you could use lambda when we're talking about waves. All right, so you wouldn't use lambda for linear expansion and so on. Just some general ideas there. So there's your wavelength lambda, and this is true for sound or light. Then we have the amplitude and so on. Now we could take this idea of the wavelength and we could go from, for example, here to here, as long as it is the distance between two identical positions on the subsequent wave, right? So it doesn't have to be from trough to trough or peak to peak. As long as you have two identical positions here, that represents your wavelength. Okay, and generally it is in meters. Now we're going to stretch a little bit and go into this idea of amplitude. And the idea of amplitude is that here it means the height of the wave, kind of. There is a term called wave height that goes from peak to trough and so on. But here it's really the displacement from what we would call the origin or the resting position of the wave. And so that does have similarities with the pendulum, because the pendulum then, we talk about its displacement from origin. Okay, and we could also talk about spring motion when we have what is called simple harmonic motion, right? So if you have a spring here with a weight, and then it opens up, and stretches, right? You have this delta x in here, and that could be your amplitude, its displacement. And then the spring would return, go back past its position, and then get compressed, right? And so you'd have another delta x here. Okay, so that's why you need to know all of this, because it's a displacement from rest. Okay, but part of the reason I wanted to talk about displacement, or the amplitude also, is because in light, when we talk about light concepts, amplitude refers to the brightness or the intensity of light. But when we talk about sound, it talks about the intensity in terms of loudness. And that also has been referred to as the intensity. Okay, so any of these concepts, yes, we're certainly going to go into light and sound here, but we have to go back to the general idea that you have a medium that is displaced from an origin, and there's a couple key terms there. So those are the basic ideas. The other terms that we're going to use, we're going to address some of those right now. Okay, so we could call this part 1, and then we could talk about part 2. What really is a wave? And we can imagine now that we have a fixed position here, and we're going to attach a rope of sorts. Okay, so we're just going to have a straight rope here, right? And the concept is that this is called a medium. And a medium is usually used to transfer. Okay? And so if you think of during Halloween or something like that, when you have the old lady with the crystal ball and she sees your future, well, that's a medium, right? She's the one who sees into the afterlife. And so messages come from the afterlife down to us, and they tell you about your life and people that you knew or whatever. So a medium is someone who speaks to the afterlife and so transfers something to you. And so a rope here could be an example of a medium. Okay, so we could have a rope or a string or a spring, for example. Okay, but you could also use some other things, and we could use air, we could use water, you could use a steel bar, for example. So all of those are an example of a medium, and now the question is, well, what's going on with the medium? So let's redraw this here. Let's draw the hook the other way, it looks a little safer. And so now we're going to use this medium, but now we're going to add energy. And that's the purpose of a wave. A wave's purpose, what waves do, is they transfer energy. Right? So it's a transfer of energy. And that energy could be, for example, kinetic energy in the form of motion. It could be sound energy, which is also kinetic energy. It could be electromagnetic, right? When we have light. We could talk about gravitational waves, for example, but we'll stick with the simple stuff here first. If I impart energy into this string or rope, then what happens is it transmits that energy. That's what waves are doing, and you need a medium to do that. Usually, you don't always need a medium, especially with these guys right here. You don't always need a medium. And so an energy here is imparted or added to this medium, and so you get this pattern here. Well, some interesting things happen when you apply energy to a medium, and we talk a little bit about sound waves later, but I want to show you some properties, though. We're going to talk about the difference between wavelength and frequency. So the idea is that wavelength and frequency often get mixed up, and so we should probably add velocity. Okay, the concept of velocity and frequency are often confused. So let's let's do this again. We're going to take a block here, put a little hook. This time we're going to put another hook next to it. Like I said, I hope that these are review items for you, but maybe not, and so that's why we want to address this. If I take a wave here or a medium and I add some energy to it, let's say that I shake it up and down, and so now I get a wave that looks like this. Now what we see is there's a long wavelength, but we don't know really much. I only know it's long if we compare it to something else. So I'm going to use a brighter color here. Now I'm going to go with orange. Okay. This time I am going to impart energy, but this time I'm going to do it more frequently. Not faster in the sense that you're thinking. I'll show you what I mean. So if I do it more, if I vibrate that more frequently, right, we could say that the orange one has a higher frequency. And then obviously the purple one has a lower frequency. And we do use this, the letter F, for frequency, but we also use this guy here, the Greek letter nu, for frequency, especially with light, not necessarily with sound. Okay, this tends to be only for light when we talk about frequency. Okay, but let's go back here for a second. They both have a wavelength and they have a frequency, but they have a different frequency. We talked about that. However, they have the same velocity. They have the same velocity within a medium. And that's going to be very important. So I hope you're paying attention to this, because while it's pretty easy with ropes and strings, it gets a little confused with light. Okay? So you have to remember this, that you have the same velocity within a medium. So now let's go back. And if we said that we go across the room, our physics room is about 8 meters long, and so we stretch a string or a rope or a compressed spring about 6 meters. And it probably only does take about 1 second to get across the room. So we could say that this goes 6 meters per second. And that's the velocity of the wave. Okay? But now we could talk about the orange one. Now we could say it's the same spring. We colored it orange so we know it's different. But if we use the same compressed spring, it still travels at 6 meters per second. Okay, so that's an important thing to know, is that the velocity within the medium doesn't change. So now if I went from a spring, right, a coiled compressed spring, right, we could say that it travels at 6 meters per second. What would happen is if we used a surgical tubing, if we use something like a rubber tube, very stretchy rubber tubing, for example, that could be as much as 3 or 4 times as fast. We actually have that in the classroom. It would be, let's say, 18 meters per second. But we could also take laundry rope, slow and sluggish, and there's not much elasticity here, and it may go as slow as 1.5 meters per second. Just some examples that the medium, the nature of the medium and its elasticity, right, relates to the wave velocity. But the frequency for these would not be related necessarily to the velocity, unless you're within that same medium. Okay, so those are some of the basic ideas between wavelength and frequency. But now if we go back here, okay, if we have to have that, remember that velocity, right, I know it's distance over time here. Okay? But we also have to know that the wavelength and the frequency are constant within a medium. So what you can say is you have the wavelength here and the velocity, right? I'm sorry. Let's go down here. If you have the wavelength, meters per second, and the frequency, that's, yeah, that would be the velocity rather. I'm sorry. That's the velocity here. We could just do V. And then you have the frequency. I'm sorry, I did that a little bit backwards, but frequency then is vibrations per second. That's a little bit different. Okay, now we can use the letter F, that's for sound. Or we could use the Greek letter nu. Either one of those. So put a big fat comma there. So we have velocity. If we, let's draw this one. This is the more common thing that you guys have probably seen in chemistry class. And that says the speed of light equals the wavelength times the frequency. This is a good way to look into this. So we have the speed of light, which is a constant in nature, and that's why it has a special letter C, is equal to the wavelength times the frequency. So why is that important? Okay, you've seen me do this before, and I want to show you again now. This C is perfect because it's constant, and it stays at 3 times 10 to the 8th meters per second. Okay? So if you have a really long wavelength, for example, infrared rays, then its frequency is going to be very small. But remember, C has to be the same. If you have a small wavelength like gamma rays, then the frequency must be really big. That's really all that's going on with our rope or our spring that we have above here. So we're going to go with the idea that the velocity equals the wavelength times the frequency. And you know I like to do this. The velocity equals 72 meters per second. And the reason I do that is because then the multiplication works out pretty well. So now if we have this equaling 72, right? We could say that we have a really small wave, 3, and we could say 3 meters per second if we want. And then we could say, well, it's 24 hertz. We'll talk about that in a minute. But that equals 72. But if you make, right, V has to be the same. But if the wavelength of 3, if it gets longer or you vibrate slower, right, you shake that rope less frequently, then we just pick a number that's less than 24, and a very convenient number would be 18 vibrations per second. You cannot do that with your hand, but you could do it with a small machine. Okay? If this is 18, we still have to equal 72, and so this becomes 4. I'm sorry, it should just say meters. Okay, then you'd have 4 times 18, and so on. So if you continue to drop the frequency, and now it's 9 vibrations per second, then this has to be 8 meters, and so on. Okay, every time it has to equal 72. Okay, so that's what's going on with the relationship between the wavelength and the frequency, is that as lambda increases, then the frequency decreases. Okay? So those are some basic examples. One more thing that we should talk about before we close the video is the concept of frequency, because this, like pressure units, is all over the place. So we really need to make sure that we understand frequency very well as we get into sound and light especially. Okay? Now we've talked about this. This is the letter F, obviously. Okay? But generally we use for sound and sometimes with the pendulum, although less often. And we're going to take a sidetrack here. Generally with a pendulum you talk about the period. And that is a capital letter T. And that is the time of oscillation. In other words, one back and forth motion. Okay, the period. And that's generally in seconds, right? That's a unit, is in seconds. But we use the time period T, a period, a length of time. But anyway, the relationship between these is that you have that and obviously this. So it really depends on what you're using. A pendulum, we don't really talk about the frequency, but with waves, we don't often talk about the period either for convenience reasons is really what it comes down to. So the idea of frequency here, also the Greek letter nu, right, is a variety of things. First of all, it could be vibrations per second. Okay? For example, when we talk about a tuning fork or something like that. And we could talk about waves per second. And what that means is when a wave is transmitted, right, in that direction, we would simply count the number of peaks that cross a certain point here, and so we could say it's 16 vibrations per second, right? So that's how we're doing frequency, is that as this wave propagates through the medium, we could count how many vibrations we experience. So you could call it vibrations per second or waves per second or events per second. Okay? Any number of those things here. But this is where it gets a little more interesting, is that it is for Maxwell Hertz. Maxwell Hertz is the one who described the idea of frequency. He didn't just invent the unit, okay? He did a whole lot in terms of waves, but we describe wave frequency in honor of Maxwell Hertz. The most common form is inverse seconds, or 1 over S, or this, right? So any number of those you're going to see in terms of frequency. So be ready for that. We could do vibrations per second. You don't often see this, but you could write it because it helps you understand the problem. You could do oscillations per second if needed. Okay, so there's some freedom in dealing with the unit of hertz. Okay, let's just make sure that you have all of the concepts here. What's important for you to learn? All right, so we have the wave vocabulary here. This is very basic wave vocabulary, but the idea that you have peaks and troughs and so on. There is a difference oftentimes with sound and light, so you want to be careful of that. Okay, and we could even talk about simple harmonic motion, but pay attention to this idea because it's going to show up later. Okay. The idea is that a wave is something that transfers energy, and so when we talk about a medium here, air transmits sound, and water could also transmit sound, as could steel. All right. You don't always need a medium, and that's a different kind of wave, but we could talk about light, how light is transmitted without a medium. Okay. The general idea is that we're transferring energy here. When we talk about wavelength and frequency here, we could take the same rope, it's colored differently so that we can make a distinction here, but if we vibrate more frequently, not faster, but more frequently, both waves travel with the same velocity within a medium, and that is something you're going to want to follow. But when we talk about their velocity to transmit from here to here, they're going to be the same velocity here. However, if we change the medium, right, from a rope to spring, rubber, and so on, then it does change the velocity. This is also true for light that might travel through glass or plastic or water, and that is definitely going to come up later on. Okay, so some of these things you've seen before: meters per second and frequency. Okay, the most common light wave equation, the most common equation rather, is here, but it relates not only to light but also to common things. So if we talked about a rope or a spring, we would have this situation here. This tells us that there's an inverse relationship between wavelength and frequency. Okay, and finally, pay close attention to the concept of frequency, because that is definitely going to be important when we talk about sound and harmonics, for example. So this is an introduction to the concept of frequency here. And like we said before, though, it does offer you a lot of options. Okay, so those are the introductory concepts and vocabulary for waves.